the end, my only friend, the end of our elaborate plans, the end of everything that's done.
Hello everyone, welcome to the beginning of Unit 8, which is our summative unit, and our summative unit covers curve sketching. So this unit is going to be broken up into 3 different mini lectures. Today we'll look at some material that covers Lecture 1. Serves as kind of an introduction to curve sketching and covers some of the basics that you need to know to sketch curves using calculus. Lecture 2 will cover an algorithm for curve sketching, and then Lecture 3 we'll look at some other methods that we can use to help us while we're sketching curves. So to start today, we're going to talk first about finding intervals of a function where the function's increasing and decreasing. So intervals of increase and decrease. So I could have some function f of x, and f of x is increasing on some interval if for any value on that interval where I can pick an x value and a second x value where the first one that I pick is less than the second one, the function evaluated at x1 is less than the function evaluated at x2. It's a simple test to see if a function is increasing or decreasing. So as an example, I could pick an x1, I could pick an x2, and if I was to graph part of that curve on that interval, I could see that my function evaluated at x1 and my function evaluated at x2, when I compare them both, x1, f of x1 is less than f of x2. So overall the function is increasing between x1 and x2. Okay, so that's how we can tell if something's increasing. F of x, or a function, is decreasing on an interval if for any values that I pick on that interval where one is less than the other, my function evaluated at x1 is greater than my function evaluated at x2. Again, if I want to show a diagram of that, I could have my value x1, my value x2, and my function could be looking something like that. And when I evaluate f of x1 and I evaluate f of x2, I can see that f of x1 is greater than f of x2. So this definition, this working definition, is good for us, but what we want to see is how can we use calculus to find these intervals of increase and decrease. So let's look at a problem to see how we can use calculus to find intervals of increase and decrease. We want to find these intervals for x to the power of 4 times 2x plus 4 all raised to the power of 5. If I looked at my definition that I previously had up, I need to pick some values, x1 and x2, to test. And I have no idea where to start just by looking at this function. But what we can do is take the derivative, y primed, and we'll use product rule. So we have 4x to the third times 2x plus 4 to to the 5th plus x to the 4 times 5 times 2x plus 4 to the 4th times 2. Simplifying, 4x to the power of 3 times 2x plus 4 to the 5th plus 10x to the power of 4 times 2x plus 4 to the 4th. And then I'll common factor. And I can common factor out a factor of 2x cubed and a factor of 2x plus 4 to the 4th. And that leaves me with 2 times 2x plus 4 plus 5x. Continuing to simplify. I end up with 4x plus 8 plus 5x. And then one last bit of simplification, my derivative becomes 2x cubed times 2x plus 4 to the 4th times 9x plus 8. So we've ended up with a derivative, a first derivative, that's all factored. So we can use this to find potential max or min points. So I get a potential max or min at x equals 0. X equals -2. Or x equals -8 over 9. These are my potential max and min points. And these are the points then that I can use to test for increase or decrease. So we're going to test some points around these max min points. And I'll do this on a number line. So I have 0, -2, and -8/9. So I'll pick a number less than -2. So let's try -3. And up with a negative factor, a positive factor, and a negative factor when I sub it into my derivative, which gives me something that's positive overall. If I have a positive derivative, then my slope is increasing. If I pick a value like -1, and I sub it into my derivative, I get a negative factor, a positive factor, and a negative factor again. So my slope is still increasing, going up. If I pick a value between -8/9 and 0, like -1/2, I get a negative factor, a positive factor, and a positive factor, which gives me something that's negative overall. So there, my slope is decreasing. And then finally, if I pick a value higher than 0, I get 3 positive factors, which is positive overall when I sub it into my derivative. So again, it's increasing. So this derivative test tells me where my function is increasing. If I look at the number line that I've drawn, I can say that my function is increasing between -∞ and -8/9, as as well, it's increasing from 0 to positive infinity. Okay, I've used a special symbol here. You might not have seen it before. That's the symbol for union. You may have seen it if you've taken data management. Union, in plain English, means and. So my function's increasing between this interval and this interval. The function's decreasing, it's going down between negative 8/9 and 0. To generalize this a little bit more, when I look at my derivatives and I break it up into intervals and I look at these intervals, if my interval for the derivative is positive, then the function is increasing. If my interval for the derivative is negative, my function is decreasing. So now we'll talk a little bit about something called concavity. Concavity looks at the shape of our curve, and to do that we're really going to think back to the parabola and learning about the parabola. So parabolas have two shapes really. Look like that, or they could look like that. The parabola that opens up we say is concave up. We know the parabola opens up when, given that equation for the parabola, a x minus h squared plus k, if the a value is greater than 0, this parabola opens up. This parabola, on the other hand, we say is concave down. If a is negative, if a is less than 0, then we end up with this parabola opening down. Let's take that vertex form of a parabola and just examine it for a second. I could take the derivative of this, even though there's no real numbers in it, bring the exponent down, multiply by that factor, decrease the exponent by 1, take the derivative of what's inside. So my first derivative for this vertex form of a parabola is 2a times x minus h, or 2ax minus 2ah. I could take the second derivative of this, my first term has a variable, so the derivative of that first term is just 2a. My second term is just numbers, so the derivative of that would be 0, so my second derivative would be 2 times a. Again, if a is positive, then my second derivative would be positive. If a is negative, then my second derivative would be negative. So I can use the second derivative to tell if something is concave up or concave down. If my second derivative is negative, I end up with a shape that's concave down. If my second derivative is positive, I end up with a shape that's concave up. Because functions can have parts that are both concave up and concave down. I can draw a function. Okay, a function that looks curvy like that. If I isolate this function into a few pieces, I can see different parts of the function where the function looks concave up or it looks concave down. looking at this function, it looks like I have two parts that are concave up and one part that's concave down. And there's points somewhere around here and here where the function stops being concave up and starts being concave down, or stops being concave down and starts being concave up. And what we want to know is, can we predict the exact point where a function changes concavity? And the answer is yes. We can find where a function changes concavity, and those changes in concavity are called points of inflection. Points of inflection are the points where a function changes concavity. If I drew a function that looked like that, see, I've got a part that's concave down, I have a part that's concave up, and right around there I would have a point of inflection. And that point of inflection happens whenever the second derivative is equal to 0. So just one more example. I'd like to find the intervals where the curve is concave up or concave down and state any points of inflection. And we'll do this for the function y equals 16 plus 4x plus x squared minus x cubed so my first derivative would be 4 plus 2x minus 3x squared. That's my first derivative. If we're testing for concavity, we're looking for points where the second derivative is equal to 0, so I'll take the derivative again. And I get 2 minus 6x. Setting this equal to 0 and solving for x. I get an x value of positive 1/3. And this x value is a possible point of inflection. I say possible because we still need to test. So I'll put positive 1/3 on the number line. I'll pick a value to the left of 1/3 and to the right of 1/3 to sub into this equation. So I'll pick 0. If I sub 0 into this equation, I get something that's positive. And we said previously that a positive second derivative means that our function is concave up on that interval. And then I'll pick a value to the right of 1/3 on the number line. I'll pick positive 1. If I sub in positive 1 to this second derivative, I get something that's negative overall. And we said previously that a negative second derivative means that the function's concave down. And now we can see that the concavity changes around 1/3, which means that our function is concave up between negative infinity and 1/3. Our function is concave down from 1/3 to positive infinity. And there's a point of inflection at 1/3, and, well, we don't know the other point. So we'll take that value of 1/3 and we'll take that value of 1/3 and we'll sub it into the original equation. Started with y equals 16 plus 4 times x, or 4 times 1/3, plus x cubed, plus x squared, so plus 1/3 squared, minus x cubed, or minus 1/3 cubed. So I get 16 plus 4/3 plus 1/9 minus 1/27. Your best bet is to do this on your calculator using your fraction button. You'll end up with 470 over 27, and we always want to keep our values exact as much as we can. So now I can say my point of inflection is at 1/3 and 470 over 27. So in this video, we have covered in the textbook 4.1 and 4.4. Your task before class is to yourself read over 4.1 and 4.4, specifically looking at intervals of increase and decrease and concavity. In class, I will do a few more examples and give you some time to practice concepts from 4.1 and 4.4.